a lineup of pregnant women, and one of them was in the bathroom. But as it turns out, none of us chose to find out the gender of our children. So out of the entire line of 7 of us, none of us knew. The first individual gave birth at the end of August to a baby boy. Oops, I started the symbol for girl. The second one gave birth at the beginning of September to a baby boy. What are the odds the third person will give birth to a baby boy? Why 50-50?
It's like 53 points.
So the event of the birth of a boy is entirely independent of the fact that the first 2 people gave birth to a boy, correct? So the odds are 50-50, regardless of what happens to anyone around that particular, like either the person in front or the person behind. Odds are independent of each other, right? Most of you will struggle with this concept in application. In theory, it sounds good, right? We all say we know it. But then, when I'm going to ask you questions about radioactive decay in a moment, you're going to use words like this. More random or less random. If something is random, it cannot be more or less random. Statistically, random is random. There is no such thing as more random or less random. That's like being more unique. That is non-existent. Either you are unique or you are not. Yes?
It's not random. It's possible.
Technically. Well, how do you say it?
The most random anything can get is a computer. That's
See, you said most random.
I know.
There are no degrees of random. Random is random. Like, you can't be more or less random. I warn you, friends, because I'm about to have you guys make a graph. I'm about to pop quiz you, too. I'm about to have you make a graph, and some of you are going to answer my questions about your graph with the terms, well, it would be more random. Have you been suitably warned? A 50-50 event, a chance event, probabilities, 50-50, will always be 50-50, which is not to say, what are the odds of the first 3 people having boys? That's a different thing, right? That's a different probability altogether. That's not the question at hand. It's, can these events that occur independently influence each other? And the answer is, Nick, I'll give you a 50-50 shot here. It's a yes or no question. What do you guys think? The answer is? There we go. So here is your task. Ready?
I'm ready.
I have given you the values of x that I would like you to graph using the following equation. So you have the values of x assigned. You should do 0, 1, 2, 3, and 4. So 0, 1, 2, 3, 4. Here's the equation I would like on this graph. I asked you to solve for the following values for x. 0, 1, 2, 3, and 4. And so I ask you to solve for what values of x? 0 through 4. So where x equals 0, then we just substitute a 0 for x, correct? And we get y equals 1. Where x equals 1, y equals 1/2. Where x equals 2, y equals, and where x equals 3, y equals 1/8. And where x equals 4, y equals 1/16. Does that look like a graph you drew yesterday? If you were to graph those points? That point is where x equals 0, y equals 1, right? One half, 1/4, etc. Agreed? If I were to start at time 0 for any radioactive substance, what percentage of radioactive atoms would remain at time 0? If I start at time 0, no half-lives have passed, what percentage of radioactive atoms remain? 100%. At time 0 in your trials yesterday, how many radioactive atoms, pennies, remained? 100. At time 1, so say 1 half-life has elapsed, what percentage of radioactive atoms would remain? If a half-life is how long it takes for half of a sample to decay, after 1 half-life, what percent would remain? 50%. Now, what's 50% in a fraction? After 2 half-lives pass, half of the remaining half would have decayed, right? What's half of a half? 25%. What does our graph tell us after 2 trials pass? We're presented with a question about radioactive decay. The easiest way to consider the question is to simply remember that equation. If I ask you about any number of half-lives, all you have to do is solve for y, and that tells you the percent remaining. Now, my problem with your graphs, at the moment, a lot of them look correct, except what always goes on each axis? A title, a label, right? The bottom is the number of half-lives, and the side is the percent radioactive sample remaining. Agreed? Is that what you saw yesterday? So, if you're ever given something with 50-50 odds and you're told like this is what it looks like, we know that we're going to have 1, then a half, then a quarter, then an eighth, then a 16th. Agreed? And instead of having to do the math in our head, we simply remember one simple equation and we can draw the graph. Tiny problem with this graph. Am I ever going to get to 0 remaining radioactive atoms? In the mathematical equation, you won't, because we'll just keep dividing in half, right? But you guys know we can't have halves of atoms, or less than a whole atom. Agreed? So in real life, this equation is only really helpful through about 4 or 5 half-lives. We don't ever graph beyond 5 half-lives because it becomes useless. That's why carbon-14, we stop using it after about 40,000 years. So, there's your definition that the guy in the video told you yesterday. It's the amount of time it takes for half of any radioactive sample to decay. This is going to be different for every radioactive atom. And yesterday, I think we said carbon-14 takes 5,730 years. So how many half-lives have passed if something is 11,460 years old? How many half-lives would have passed? How do you know? Should I write the number? Better? Now can you explain it? How do you know it's exactly 2? It's what you did in your head. What did you do? So you took 5,730 and just added it? Or could I simply say, and what do you get? What percent of radioactive carbon-14 remains then? If 2 half-lives have passed? You have 2 ways to solve that. Either consult your graph or use the equation. What's the equation you would use? Where x represents number of half-lives. So if that's true, what percent remains? 25%, a quarter, right? Let's try this one. How would you solve it? Go ahead and solve it with your partners on your whiteboard. Oh, this is a total math teacher thing to do. Show your work.
Wait, you're not asking
Not yet. Rest of you, follow-up question. What percent of potassium-40 remains?
You have